Hello everyone, welcome back to my channel. My name is Ayushman. Today I will be presenting my research on logic in memory operations using ternary NAND NOR universal logic gates in double gated feedback field effective transistors. Here we will be studying about emerging technologies which are blending logics and memory operations to push computation and boundaries. Now let's get started. We use the research paper by Willie VCH 2023 model. Hence, now the first slide which shows us introduction to the ternary logic. Here we are familiar with the binary logic where computations were on two states which were 0 and 1, however which we know. However, the ternary logic introduces a third stage typically denoted as -1, 0 and +1. This third state reduces the number of logic operations needed, leading to the simpler circuits and potentially faster processing it provides. This is important as modern applications while doing performance or energy efficient as a key. Here we have used many ways, like first we use the traditional logic systems which shows 0 and 1 as the values. Then on the basis of introduction we explored the third state which we can use as -1, 0 and +1. Then what are the more advantages we can say is the reduced complexity, improving the processing efficiency as it can increase the speed of the work, or however power saving is also it can be considered. Next, now logic in memory concept is a powerful concept that aims to reduce the need for frequent data transfers between the processor and the memory. By performing logic operations directly within the memory, we can achieve significant improvements in both speed and energy efficiency. This becomes even more potent when combined with ternary logic, as it allows for denser, more efficient computational architectures. As we can see here, we have mentioned the 5 points which logic in memory concept includes: logic in memory, speed enhancement, then integration with ternary logic, reduced data transfer, and power efficiency. These are the points which logic in memory gives us with the advantages which we can say. Now, field effective transistors, or we can short form we say FET. Let's now briefly touch the field effective transistors which are widely used in digital circuits to control the flow of current. FETs are used to control the flow of the current. In our case, we are focusing on a particular type of field FETs which are called as double gated feedback field transistors, which we are saying as DGFBFET. These are advanced transistors are key to implementing a ternary logic, allowing to control multiple states within a single device. Within a single device, we are using multiple transistors or multiple ternary logic so that we can implement more and more. The role of FETs in digital circuits we are showing, then introduction to double gated feedback field effective transistors, then feedback mechanisms, then applications, then importance what we are studying now. Now let's go to next slide. Double gated feedback FET. FET means we know that FET we studied backwards. So now operational mechanism, lower power consumption, compatible device footprint, and high speed operation which we know. DGFEFETs have unique feedback mechanism which makes them ideal for the multi-state operations like ternary logic. The double gate allows for the greater control over the states, enabling for more efficient computation. The technology also helps in lowering the consumption, the reducing the size of the devices are the important advantages for the modern electronics. As we can say that double gated feedback are more lower power consumption. They consume less and less power according to the field effective transistors. So that's why we are using DGFETs more than the FETs. High speed operations, compact footprints, operational mechanisms. Then the feedback mechanism which is new in this is the plus point which we can say which can be ideal for the multi-state operations like ternary logic. Now next, ternary NAND NOR logic gates. Now fundamentally we are studying about the ternary NAND and NOR which are crucial because these are the universal gates. You can build any of the using them. With ternary logic, these gates are designed to work with three possible states: -1, 0 and +1. In this research, DGFBFETs are used to implement these gates, allowing for a seamless execution of ternary logic. Here a quick look of the truth table of the ternary NAND and NOR gate. As we are giving as out input -1, the output comes output as +1. We are giving the input as -1 0, the output comes out +1. We give -1 +1, the output comes 0. We give 0 -1, then output +1, and so on. We can see. Now, circuit design and the simulation. Next, we'll come to the actual circuit design and the simulations by using DGFBFETs. We can design circuits by directly performing logic in memory operations with the ternary logic. The simulation results validate that the ternary NAND NOR gates functions are expected, offering a glimpse that functions are as expected, how circuits could outperform traditional binary designs metrics such as speed and power consumptions. Here we can see in the circuit design we are generally seeing 3 points: speed matrices, power consumption comparisons, and device size advantages. In the speed, as we know, DGFBTs, we are talking from the previous 2-3 slides, as it is the faster execution in the logic operations and reduce the propagation delays. Then the power consumption comparisons we are doing, it consumes less power. So that's the point. Ternary NAND NOR operation consumes significantly less power than the binary, enhancing energy efficiency. Device at DG efficiency also have the advantages of device size at its compact circuit design. It can be easily set up in a normal any device. Then, so why ternary logic with DGFBFETs? First, ternary require fewer transistors to perform the same operation compared to binary systems. This leads to higher computation density, which means more processing power in smaller space. Additionally, these systems use less energy, making them ideal for the application where efficiency is critical, such as mobile devices and wearables. These are the advantages like energy savings, enhanced computer density, fewer transistors operations, then efficiency of digital is good. Then challenges for the futures and directions. Of course, there are challenges. Fabricating DGFBFETs on a large scale is complex, and we still need to optimize their reliability. Additionally, there are potential issues with scaling their technology for mass production. However, the future looks promising. Researchers are exploring ways to improve performance, reliability, and the technology could pave the way for the more complex operations. Now, challenges which we are further facing is scaling issues, reliability concerns, performance metric improvements, exploration of complex logic operations, then integration with the semiconductor technology.